Okay, this is Math 131, Section 3.3. First, we're going to talk about the conditional statement. Remember, that's an if-then. So, conditional statement, we have P arrow Q. And that's true in every case except when P is a true statement and Q is a false statement. So, the only time that this is false is when we have a TF. You know, the T, in other words, let's say, remember I said if you pass the exam, then you'll pass the class. Case one is you pass the exam and you pass the class. You did what I asked you to do and you passed the class, so that's true. Okay. Case two, you passed the exam, but you didn't pass the class, and I said you would, so that's false. I lied to you. Okay. In the case three and four, you didn't pass the exam, but I didn't say what would happen if you didn't pass the exam. I just said if you did pass the exam, you'd pass the class. So if you didn't pass the exam, you could either pass the class or not. Q could be true or false, and it still wouldn't violate the if-then, the conditional statement, because the conditional only addresses if you pass the exam, you know, P. Doesn't say what happens if you don't pass the exam, so either one could happen if you pass the exam, if you don't pass the exam. Okay, so the only case that we get false is when you have a T arrow F. Okay, so let's look at a truth table for this statement. Negation P, if negation P, then negation Q. So remember with the truth table, we have to look at all four cases because we have two simple statements, P and Q. Okay, so here's our truth table. Remember, we do TTFF for P and then do TFTF for Q. So we've got every possible case. When P is true, then negation P is false. So we have TT and then becomes FF here. And then when P is false, negation of P becomes true. So we're going to write these out first, negation P. And then we also need negation Q. So negation Q would be FT, FT. We just change those to the opposite. Okay. And then we're doing the arrow between the two. So remember, the only thing that gives us a false is a TF. FF would be true. FT would be true. TF is the only one that gives a false, and then TT gives us a true. So this would be our truth table for negation P. If negation P, then negation Q. Okay. So we're putting our answer underneath the arrow there. Okay, the biconditional statement means if and only if. So P if and only if Q. Okay. So remember I said in class that means that if P then Q and if Q then P. Okay. So we can write that using symbolic logic at this. P if P then Q, parentheses, and if Q then P. Okay. In other words, if I say you will pass the test, pass the class if and only if you pass exam 2. Okay. That means two things. That means if you pass exam 2, then you'll pass the class, and if you pass the class, then you must have passed exam 2. So it goes back and forth. You know, they go hand in hand together. Okay, so these are true when P and Q are both true. Okay, and when P and Q are both false. Okay, so they have to be the same. In other words, a TF will give us a false, and an FT will give us a false. Okay. So if we look at P arrow Q, if they're the same, sorry, if we're looking at the biconditional, we would look at them both being the same to give us a true. Okay. And then if they're different, we have a false. Okay. So let's look at the parts there. Remember P arrow Q would be true, false, true, true, because that's only false when we have a TF. And then Q arrow P, we're going backwards now. So here's our Q, here's our P. So this is true. False, true would be true. True, false is the only one that gives us a false. And then false, false gives us a true. Okay, we're talking about Q arrow P, and this is our Q, and this is our P. Okay, so now we're going to take the and of these two. We're doing kind of showing how, you know, we can do the biconditional by putting these together. Okay, so true and true gives us true. False and true gives us false. Remember, they both have to be true for an and. True and false gives us false. Okay, and then true and true gives us true again. So there's our truth table. We don't have to break this out every time, but we're showing you how you know what it really means when we say if and only if, that there's two things, P arrow Q and Q arrow P. Okay, and we do that, we get true when they're both false or when they're both true, but otherwise it's false if they're true, false, or false, true. Okay. So just to summarize, the biconditional statement P if and only if Q is true only when P and Q have the same truth value. Okay. In other words, both are true or both are false. Okay, so let's look at truth table for something using a biconditional. We have negation P, if and only if, and then in parentheses, negation Q, if, negation Q, then R. It's kind of hard to say that, but we would say negation P, if and only if, negation Q, then R. Okay, we have a comma before that last statement. Okay, so we have 3 simple statements, so we're going to have 8 lines, right? We're going to have 8 different cases. So start with P and do all trues first, so 4 T's and then 4 F's. Then Q, we're going to go by 2's. Remember I said we do 4, 2, 1, so we do 4's, true, false, then 2's, so we're going to do 2 trues, 2 false, 2 trues, 2 false, and then for R we just do TF, 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 TF. Okay, and that sets up our truth table. Okay, now we're going to take negation P, so we have 4 trues and 4 falses, so that gives us 4 falses, 4 trues. Okay, negation Q would give us false, false, true, true, false, false, true, true. We're changing these to the opposite. R we're just copying over. Okay, and then we're going to do the parentheses first, so we're going to do negation Q, if negation Q, then R. Remember, the only thing that gives us a false is a TF. So FT gives us a true, FF gives us a true, TT gives us a true, TF, there's a false, FT would give us a true, FF would give us a true, TT would give us a true, and then TF would give us a false again. Okay, so this is our truth value for the if-then that's in the parentheses. Okay, now we're doing a biconditional with that. So we're doing this thing, negation P, with this thing. Okay, which is the conditional we already did. Okay, remember it's false if they're different. It's true if they're the same. So FT is different, false. FT, false. FT, false again. FF, true. TT, true. TT, true. TT, true. And then finally TF, false. So this would be our biconditional, our last answer there. That would be the truth table for that compound statement. Okay. And you can see the steps are numbered here. That would be the first step, second step, third step, fourth step, fifth step. Okay, so let's look at an example. We have a graph in the next slide that represents student population by age group in 2013 for the State College of Florida. Okay, and we want to use the graph to determine the truth value of the compound statements that are given. Okay, so here's our graph. This is just student population, 44% younger than 20, 41% 20 to 29, 8% 30 to 39, 5% are 40 to 49, and 2% are 15 older. Maybe somewhat similar to U of M Dearborn's population, maybe a little bit larger in some of these pieces for U of M. Okay, so we're going to determine the truth value of the statement. If 44% of the State College of Florida population is younger than 20, or 38% of the population is age 20 to 29, then 8% of the population is age 30 to 39. So we're going to have to come up with some simple statements to represent some of these things and then determine the truth value. Okay, so here's our simple statement setup. P will be 44% of the SDF population is younger than 20. Q will be 38% of the population is 20 to 29, and R will be 8% of the population is age 30 to 39. So our original statement was 44% of the population is younger than 20, or 38% of the population is 20 to 29. If that is true, then 8% of the population is 30 to 39. Okay, so this is how we would translate that into a compound statement. Okay, so let's look at the truth value of each of these statements based on our graph. 44% of the State College of Florida population is younger than 20. Okay, if we look at that, yes, it's true. Okay, so P is true. So I'm going to put the truth value below that for P. Okay, and then the next thing is 38% of the population is 20 to 29, and we can see no, that's not true. That's 41%. So that would be false for Q. So Q is false. So I'm going to put an or and then false. Okay, and then arrow, and let's look at R. Okay, so R says 8% of the population is 30 to 39, and if we go to 30 to 39, I know it's small type, we do have 8% there, so that R is true, so we're going to put in true for R. So basically I just inserted the truth values for P, Q, and R. P is true, Q is false, and R is true. Okay. So if we put in the truth values, we don't have to do a truth table because we know the truth values of these. We can determine it from the graph, right? So we just have to basically looking at one line of the truth table. So we have true, false for Q, and true for R. So we have true or false. Remember, or just one of them has to be true. So this parentheses would be true. And then we have T, arrow T, or true arrow true. And remember that for the conditional that gives us the true. So the original statement is true, and we just showed that using symbolic logic. Okay, let's look at another statement. 5% of the population is age 40 to 49, and 5% of the population is age 50 and older, comma, that's a grouping symbol, if and only if, biconditional, 41% of the population is 20 to 29. So we're going to make simple statements here, translate to symbolic logic, and look at the truth value there. Okay, so we'll make P be 5% of the population is 40 to 49. Q would be 5% of the population is age 50 or older, and R would be 41% of the population is 20 to 29. Remember, we're saying if P and Q, or R if and only if P and Q. Okay, so we can say 41% of the population is 20 to 29 if and only if 5% is age 40 to 49, P, and 5% of the population is 50 or older. So we're going to translate that statement into this in symbolic logic. P and Q, comma. Remember we had a parentheses because we had a comma in this statement. If and only if R. Okay, so let's look at the truth values of those. First statement, P, 5% of the population is 40 to 49. If we go to 40 or 49, we have 5%, so P is true. Okay. Okay, now let's look at Q. So Q says 5% of the population is age 50 or older. And if we go to 50 and older, no, it's only 2%. So Q is false again in this one. Okay. And then we have if and only if, just carrying that down. And let's look at R now. R says 41% of the population is 20 to 29. If we go there, it's true. So R is true. Okay. So we have T and F, parentheses, if and only if T. So if we look at that, just P is true, Q is false, and R is true. T and F, remember they both have to be true, so that's false. Okay. And then we have false, if and only if T, and remember, if and only if means they both have to be the same to be true, so this statement is false. Okay, let's look at some terms. We talk about a self-contradiction. That's a statement, compound statement. It's always false. Okay. So we're going to say every truth value in every column of the truth table is false. Okay. We call it a self-contradiction. So we would have to get all falses to get a self-contradiction. If we get one true, it's not a self-contradiction. So there is a case where it's true, then it's not a self-contradiction. So with the self-contradiction, we say it's false in every possible case. So as an example, let's look at this statement. If P if and only if Q, and P if and only if not Q. Okay. Now think about that in terms of like if you pass the exam and you pass the test, pass the exam, pass the class. So you will pass the class if and only if you pass the exam, and you will fail the class if and only if you pass the exam. Now that doesn't make sense, right? That seems to be, like it looks like a self-contradiction. So let's look at the truth value of those, and we're going to have 4 cases because we have 2 simple statements. So here's our truth table using P, T, T, F, F, and then Q, T, F, T, F. And then we're going to look at P, double arrow, Q first, so biconditional. So true, true gives us a true. True, false, false. False, true, false. And false, false gives a true. Remember, we're just looking for them to be the same to be true. Okay, either both true or both false. Okay. Then we look at P, biconditional negation Q. Let's put negation Q over here since it's not in there. I'll put it in there so we can take a look at it. So that would be false, true, false, true. I'm going to change Q to the opposite. Oh, there it is. I'm sorry. I didn't see it. There's false, true, false, true. Okay, and here's P. So they carry that over. And we're doing double arrow with this, right? So biconditional means they have to be the same to be true. So they're different, false, same, true, different, false. Okay. So now we've got this biconditional done and this biconditional done, and we're taking the and of those two. Remember, and they both have to be true. So not both true, so false. 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 So notice we have F's all the way down. So this statement is a self-contradiction. In other words, we say it's a self-contradiction or it's a logically false statement. It doesn't make sense. Can't happen. Okay, a tautology is just the opposite. That's a compound statement that's always true. Okay, so when every truth value in the answer column of the truth table is true, we call that a tautology. So we have to make sure we have all T's all the way down. Okay, so let's look at this compound statement. We have if P and Q, then P or R. Okay. So now we have 3 simple statements, so we're going to have 8 lines for this. Okay, so our truth table, remember we start with P's and we do 4 T's and then 4 F's. Then for Q we do 2 T's, 2 F's, 2 T's, 2 F's. And then for R we do TF, 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 TF. Okay, and then we get that if we do that pattern, we get it in the right order. Okay, so we're going to look at P and Q first. Both have to be true. So TT gives us true. TT gives us T. TF gives us F. TF gives us F. FT gives us F. FT gives us F. FT gives us FF gives us F, and then FF gives us F. So we need both true in order to be true. So the only two ones that are true are the first 2 for P and Q. P or R, now we just need 1 true. So P or R, true or true gives us true. True or false gives us true. True or true gives us true. True or false gives us true. False or true gives us true. False or false gives us false. We don't have any T's. False or true gives us true. And then false or false gives us false. Okay, so those are the truth values for P or R. Now we're going to take the conditional of those 2. This one, or if this one, then this one. Okay, so remember, TF is the only one that gives us a false. TT gives us a true. TT gives us a true. FT gives us a true. FT true. FT true. FF gives us true. FT true. FF true. Notice in that last step, they're all true all the way down, which means this statement is a tautology. Okay, or we can say it's a logically true statement. It's always true. Okay, sometimes we say that's an identity in math. That's always the case. Okay, and then we talk about an implication. That's a conditional statement. That's a tautology. Okay, so the consequent, the then part will be true whenever the antecedent is true. Okay, so we could say maybe if you're breathing, then you're alive. Something like that. That's always true, right? That it's implied that if you're breathing, you're alive. So once we say it's an implication, that means that the then part is implied by the if part. Okay. So here's a compound statement. Notice it is a conditional because it has the arrow here, but we've got a pretty complicated if part, right? If P or Q and negation Q, then P. Okay. Let's kind of do this with the exam thing again. So if you pass the exam or you pass the class and you don't pass the class, then you pass the exam. Now these two don't really matter, right? If you think about it, we're saying if you pass the exam or you pass the class and you didn't pass the class, that means that this has to be true because you can't have both of these happen. You can't say, oh, that this is true and this is true. You can't say you passed the class and you didn't pass the class. So that implies that P is true here. And that means, well, that P is true. So let's look at the truth value of this, and just to show that, this will give us all true values. Okay, so here's our truth table, T, T, F, F, T, F, T, F. And then we're going to look at P or Q first. Okay, so P or Q would give us just need one t, so we have true here. One t, so we have true here. One t, true. And then no trees, so false. No t's, so false. And then we need negation cues. So TF becomes FT. Okay. And then we're taking the and of these two. Okay. So first step, do the or. Second step, take the negation of Q. Third step, we're going to do the and of these two. Okay. So they both have to be true. So T and F gives us F. T and T gives us T. T and F, F. F and TF. Okay. So we have this FTFF for the and. Okay. Now we're going to carry P over and do an if-then with this and this. So remember, the only thing that gives us a false is TF. FT gives us a true. TT gives us a true. FF gives us a true. And then finally FF gives us true. So we can see that that's always true. So we can say this statement is a tautology, and because it's an if-then, we call that an implication. In other words, the if part implies the then part. Okay, we'll look at some more examples in class in more detail, but hopefully you get a general idea of what we mean by implication and tautology and self-contradiction.